So, we've talked about how problems can repeat themselves, and we've looked at how to control complexity. But here's the thing. Before you can search efficiently, before you can optimize intelligently, you have to impose order. Today, we're diving into why sorting isn't just about making your data look neat, it's about unleashing its true potential and unlocking a whole new level of speed and power.
Yeah, and that right there, that's the heart of what we're talking about today. The simple act of putting things in order is one of the most powerful, most transformative things you can do in all of computer science. It's a fundamental shift in what's even possible.
So let's get right into it. What is sorting, really? Well, it's so much more than just arranging items on a list. It's kind of like alchemy, turning total digital chaos into structured, usable information.
You know, think of it this way. Sorting isn't just about shuffling things around. It's like you're hacking a path through a dense, tangled forest. And all of a sudden, what was once this impenetrable mess becomes a clear, easy-to-navigate road. And the results? Whoa. They are immediate, and they are absolute game changers. Suddenly, you can use something like a binary search to find anything in a flash. Finding duplicates, that becomes trivial. And a whole class of really difficult problems, their complexity just melts away. Sorting is without a doubt a massive power-up for your data.
Okay, so let's really see this in action. The difference between unsorted data and sorted data. Honestly, it's like night and day. It's a total transformation in what you can do.
Just look at this comparison. With a pile of unsorted data, you're basically lost. If you want to find anything, you have no choice but to check every single item. There are zero shortcuts. But once it's sorted, bam! Patterns just jump out at you. You instantly know that everything to the left of a 5 is smaller and everything to the right is bigger. You could just ignore huge chunks of the data. You can eliminate possibilities. And that right there is the very heart of efficient computing.
So here's the crucial insight. The order itself is information. By the very act of sorting the data, you've added knowledge to the system. You've created relationships. You now know something about how every single element relates to every other element. And that knowledge is exactly what makes everything else so much faster.
So how do we actually pull off this magic trick? Well, it turns out that behind all the really complex and fancy algorithms, there are really just two simple, super elegant ideas at play.
Okay, so on one hand, you've got what we call incremental ordering. The whole mindset here is pretty straightforward. You take one item at a time and you just put it where it belongs in a growing sorted section of the list. Simple. On the other hand, you have divide and reassemble. This strategy is totally different. It doesn't care about final positions at the start. It just breaks the problem down into smaller and smaller pieces, sorts those tiny pieces, and then cleverly merges them all back together. One builds up, the other breaks down. All right. Let's take a quick spin through 4 classic algorithms just to see how these two core ideas actually play out in the real world. This is going to show us the different trade-offs you have to make when you're trying to create order. First up, the one everybody learns about, bubble sort. Now let's be real, it's slow. O of n squared slow. You would almost never use it in a real-world application, but its value? It's purely educational. It perfectly teaches the absolute basics. You compare 2 items right next to each other, and if they're in the wrong order, you swap them. You just keep doing that over and over. It's great for teaching you how sorting works, not how to sort fast.
Next, we've got insertion sort. This is a lot like how you'd probably organize a hand of playing cards, right? You pick up a new card and you slide it into its proper spot. Now, while it's also ON scored in the worst case, it has a secret weapon. It is blazing fast on data that's already mostly sorted. This little trick makes it a key component inside some much more advanced algorithm.
Now for merge sort. This is the poster child for that divide and reassemble idea. It just keeps splitting the data in half, over and over, until it can't be split anymore. Then it perfectly merges those tiny pieces back together in the correct order. Its biggest strength is its consistency. It is always ON log n. No ifs, ands, or buts. It's the reliable, totally predictable performer.
And now we get to the king of the sorting world, the one you see everywhere, quicksort. Quicksort is a bit of a gambler. It makes a really smart bet about how to split the data, and almost all of the time, that bet pays off, big time. That's why, even though there's a tiny chance of a really bad day, it is the go-to workhorse for so many real-world systems. It's a great reminder that sometimes a smart, calculated risk is the fastest way to get things done. And looking at them all together like this, it just brilliantly lays out the whole landscape of trade-offs. You're balancing speed against consistency, simplicity against raw performance. There's just no single best sort. If you need an absolute guarantee on performance, no matter what, merge sort is your friend. But if you're dealing with a small list that's almost in order already, hey, insertion sort might actually be faster. The right choice always depends on the job.
And this just nails the mindset of practical software engineering, doesn't it? We don't use quicksort just because it has a cool name. We use it because for a huge number of common problems, it's the right tool for the job. The goal is to solve a problem efficiently, not to be a purist about one particular approach. Okay, so this is where it all comes together. Here is the big, critical takeaway. Sorting isn't just another tool you pull out of the toolbox every now and then. In the world of high-performance systems, it's the very foundation that everything else is built on. And that brings us to a few common myths we really need to bust. First, just because an algorithm is asymptotically faster on paper doesn't mean it's actually faster in the real world on a small dataset. Second, the cost of doing a sort has to be worth the speed you gain later on. Third, something called stability really matters for complex data. It makes sure items with equal values stay in their original relative order. And finally, some friendly advice. The sorting functions that are built right into your programming language, use them. They have been incredibly optimized by absolute experts.
And that all leads us to the golden rule for anyone who works with data. You absolutely need to understand the principles of sorting, you need to know the trade-offs, and you need to get why it's so important. But you should almost never ever write your own sorting algorithm from scratch for production code. Know what tool to use, and then use it well.
And look, this isn't just some abstract theoretical idea, right? This principle of pre-sorted data is the absolute bedrock of the technology we all use every single day. The reason your database can find one record in a table with 1 billion rows and do it instantly, it's because of massive pre-sorted indexes. The efficiency of our operating systems, our data streams, transaction logs, it all comes back to this fundamental principle. Without it, complexity just explodes and our digital world would grind to a halt. At the end of the day, sorting is how we make raw data navigable. It's how we allow our systems to reason about information efficiently. In computation, just like in so many other things, order isn't just a nice-to-have. It is the very foundation of intelligence itself.